To introduce a system of equations, I would like to start with an example from an ancient Chinese mathematical book dated more than 1,500 years ago. The title of the book, when translated into English, is The Mathematical Classic of Sun Zi, or Master Sun, and he should not be confused with the author of the famous book The Art of War. Here is the translation of the problem. In a yard, there are chickens and rabbits. Together, there are 35 heads and 94 feet. And the question is, how many chickens and how many rabbits are there? If you are interested, I encourage you to try to figure out what was the method and solution given in the original book. But this is actually a very typical problem that can be solved by setting up a system of equations. Let's use x to represent the number of chickens and y to represent the number of rabbits, and see what kind of equations we can write based on our understandings of chickens and rabbits. Since together there are 35 heads, that means that the total number of chickens and rabbits must be 35. Therefore, we can write our first equation that x plus y equals to 35. Also, since each chicken has 2 feet and each rabbit has 4 feet, and the total number of feet is 94, therefore we can write the second equation that 2 times x plus 4 times y equals to 94. Now, to find the solution to this problem, these two equations must be satisfied simultaneously, and this is known as a system of equations. Particularly, this example is a linear system of equations with two variables. As you can see, we only have two variables here, x and y, and this is a linear system because both equations are linear equations. In other words, the graphs for both equations are straight lines, as we learned a long time ago. There are many methods to solve for a system of equations, and in this video we will introduce one of the most basic methods, method of substitution. For convenience, let's number our equations, equation 1 and equation 2. And the first step is to solve for one variable from one equation as an expression of the other variable. It is up to you to decide which equation you want to start working with first, and also which variable you want to solve for first. You want to make that decision that will make your calculation easier. In this case, I'll just start working with equation number 1, and I will solve for variable x first. So from equation 1, x solved as an expression of y is 35 minus y. And let me call this equation 3. The next step is to substitute equation 3 into equation 2 and solve for y. And this is why this method is called method of substitution. And also, if you substitute equation 3 back into equation 1, that would not be very helpful, and you should be able to tell why. So after we substitute equation 3, which is x equals to 35 minus y, into equation 2, this is what we get. And as you can see, we have one equation but with only one unknown, which is y, and we can solve for y to be 12. And then for step 3, we solve for x from equation 3. Since y equals to 12 and x equals to 35 minus y, therefore x equals to 23. And now we have our solution to this problem, that x equals to 23, which means that we have 23 chickens, y equals to 12, and that is 12 rabbits. And it's always recommended to double check your solution by substituting your x and y values back into the original equations. And after the calculation, as you can see, the two equations are indeed satisfied simultaneously. And that is the solution to this example. Let's look at this example. We have another linear system of equations with two variables x and y. And we're going to solve this problem using the method of substitution again. So we number these two equations, 1 and 2. And for the first step, if you recall, we need to solve for one variable from one equation, and it is up to us which one we want to work with. From observation, it looks like it's more convenient to solve for y from equation 2, and that is y equals to 3x minus 13. Let's call it equation 3. For the next step, we're going to substitute equation 3 into the other equation, since we used equation 2 to get equation 3. Therefore, we do not substitute equation 3 back to equation 2, but we substitute it into the other equation, in this case equation 1, and try to solve for x. Therefore, equation 1 becomes thus with y substituted by 3x minus 13. Again, that makes one equation with one unknown x, and we can solve for x to be 6. And for the last step, we solve for y from equation 3. Since x equals to 6, and according to equation 3, y equals to 3x minus 13, therefore y equals to 5. So this pair of numbers, x equal to 6 and y equals to 5, is the solution to this linear system of equations. And you can substitute these two numbers back into the original equations and double check to see if the two equations are satisfied simultaneously. Earlier I mentioned that this is called a linear system of equations because both equations are linear equations. And we learned how to plot linear equations before, and here we're going to plot both equations on the same xy rectangular coordinate system. This blue line is equation 1, and this red line represents the graph for equation 2. Now, if we only need to solve, say, equation 1 individually, then every single point on this blue line represent a solution point of this equation. Therefore, there are infinite number of solutions to equation 1 alone. Similarly, there are infinite number of solutions to equation 2 alone. However, for a system of equations, we are looking for x and y values that will satisfy these two equations simultaneously. And on the graph, we are looking for the point or points where these two graphs intercept with each other. In this case, we only have one intercept point, which is 6, 5. And 6 is the x coordinate of this point, and 5 is the y coordinate of this point. So again, the solution to this system of equations is x equals to 6 and y equals to 5. As you can see, there is only one solution. The method of substitution can be used to solve for nonlinear systems as well. If any one of the equations is not a linear equation, then the system is a nonlinear system. Like in this example, we have two equations, equation 1 and 2. As you can see, equation 2 is indeed a linear equation. However, equation 1 is not. Therefore, this is a nonlinear system. So again, let's follow the same procedure. Step 1, we solve for one variable from one equation. For convenience, based on our observation, it looks like it's easier to solve for y from equation 2 as an expression of x, which is negative 3x minus 9. Then step 2, we want to substitute this equation 3 that we just derived into the other equation that we didn't work with, which is equation 1, and then solve for x. So equation 1 now becomes this, with y substituted by negative 3x minus 9. And this is one equation with only one unknown. And after rearrangement, as you can see, this is a quadratic equation that we are very familiar with. And we can either try to factorize it, or we can try to use the quadratic formula. Either way, There are two solutions. X can be negative 4 or X can be positive 1/2. Same step 3, we solve for y from equation 3. Since we have two values for x, correspondingly, we should have two values for y as well. Y equals to negative 3x minus 9 when x equals to negative 4, y equals to 3, and when x equals to 1/2, y equals to negative 21/2. Therefore, the solutions to this system are two pairs of numbers, x equals to negative 4 and y equals to 3 at the same time, or when x equals to 1/2 and y equals to negative 21/2. Again, we can try to plot both equations. Equation 1 is a quadratic equation, therefore its graph is parabolic, and equation 2 is a linear equation, therefore its graph is this straight line. Once again, we're looking for solution points that are both on equation 1 and on equation 2. Therefore, we're looking for the intercepts, and we have 2 in this case. This is the first one, corresponding to when x equals to negative 4 and y equals to 3. And this is the second one, when x equals to 1/2 and y equals to negative 21/2. And these two also agree with our solutions that we got from the previous steps.